The solar wind is a globally neutral gas composed of charged particles. Empirical evidence shows that it is warmer than expected. One of the most important contemporary subjects in space physics is the problem of the heating of the solar wind plasma. Scientists have suggested that the cause of this heating may be the turbulent cascade, but what is the turbulent cascade and how does it act to heat the solar wind? When stirring a cup of coffee with a spoon, swirls and vortices are produced in the liquid. These vortices split into smaller and smaller eddies until, at the smaller scales, the motions dissipate and the energy turns into heat. It would now seem that stirring heats the liquid, while everyone knows that the effect of stirring is to cool the coffee. In fact, the vertical motion triggered by the spoon brings layers of hot coffee from the bottom of the cup up to the surface, where they come into contact with the cold air, which absorbs the heat. As a final effect, the coffee cools off. But there is no cool air in space, and here is the difference between the coffee and the solar wind. As for the coffee, the energy injected by the sun stirs the solar wind, producing vortices and swirls. Along the turbulent cascade, the energy within these vortices eventually reaches a smaller scale and dissipates into heat. At this point, the temperature shoots up, and there is no cool air to stop it. Nowadays, modern supercomputers provide a unique opportunity to run multi-dimensional kinetic simulations of plasma systems. Recently, a massive scientific research activity developed within the PRAISE project 3D-3V Vlasov simulations of plasma turbulence has been devoted to performing numerical simulations of realistic physical conditions of the solar wind environment, with the purpose of providing clues for the identification of the physical processes at work in the turbulent interplanetary gas. The numerical tool adopted to develop this line of research is the hybrid Vlasov-Maxwell code, which integrates the Vlasov equation for protons in 3D-3V phase space. The algorithm maps the domain to a grid which is discrete with respect to time, space and velocity, and uses a Eulerian approach to interpolate between those points. The code has been massively parallelized in the physical domain by distributing the particle distribution function among the processes. This animation shows the time evolution of the magnetic field during the development of the turbulent cascade. This turbulence leads to the generation of coherent structures and magnetic islands which are not static but evolve in time. As they interact non-linearly, the magnetic field between them becomes very intense and its topology is broken and local magnetic reconnection events can occur. The presence of these high magnetic stress regions is a signature of the intermittent nature of the magnetic field. This animation shows the time evolution of the density fluctuations as the turbulent cascade develops and transfers energy from large to short wavelengths. In the simulation, the cascade is initially triggered by injecting energy into the system which set equilibrium as large-scale fluctuations. To be specific, the typical scale of the initial perturbations is a little larger than the proton inertial length. The initial condition of the simulation looks like a sea of large vortices and swirls. As is shown in this video, over time, these structures interact non-linearly as they attract, repel and merge. As a result of these non-linear interactions, the vertical structures fragment, giving rise to new vortices of smaller and smaller size. This is the so-called turbulent cascade. This sequence shows how the proton velocity distribution, or PVD, looks in a turbulent medium. In the box on the left, the density fluctuations are represented at the end of the simulation when the maximum level of turbulence has been reached. Many islands and swirls can be recognized in this volume plot. A cursor moves within the three-dimensional turbulent pattern. For each spatial position explored by the cursor, the corresponding three-dimensional PVD is displayed in the box on the right. It is clearly visible that the shape of the PVD appears distorted with respect to the typical Maxwellian shape of thermodynamic equilibrium, i.e. a sphere in three-dimensional velocity space, and more resembles a deformed potato. Moreover, the shape of the PVD changes according to the spatial position of the cursor. This evidence supports the idea that kinetic effects responsible for driving the system far from thermodynamic equilibrium are not homogeneously distributed in space, but act differently depending on the local spatial features of the turbulent pattern. Since we have some time left, we'll now talk about the steps that we took to bring this project to realization. Our first task was to extract the raw data from the files provided by the researcher. The files contained unformatted row data, with each row containing six ASCII floating point numbers representing the components of the electric and magnetic fields. PowerView cannot read such files directly, so we had to convert the files into a format that PowerView can read. I prepared a script that read in the raw data and rewrote it in the format of legacy VTK files. We found that PowerView read this data very slowly, so we converted it from ASCII to binary. We also found that PowerView is quite inconsistent in extracting scalar values from vector fields, so I rewrote the data files to include vector data along with scalar data for each component of the vectors and their magnitude. This meant a lot of repetition, but also that the full complement of visualization options was available. We then spent some time familiarizing ourselves with the various ways in which data can be visualized in PowerView. Surface and volume plots being the main way in which scalar fields are realized, and more elaborate options such as streamlines and glyphs being available for vector fields. We also wrote PowerView macros to prepare some of these visualizations automatically, and got used to PowerView Python syntax. We then spent some time considering the possibility of making a custom PowerView-based application to display the data, discovering that it was impossibly complicated, or a bespoke plugin, which turned out to be merely impractically complicated, before deciding to stick to macros.
Hi, I'm Jasper. My work on the project mostly consisted of writing a PowerView macro for the last part of the visualization, the velocity distribution video. The PowerView part might seem simple, just finding a consensus between 5 people over which picture looks the nicest. The hard part and the motivation behind working out a specific script or macro was the fact that the massive computation was done on Seneca's Fermi cluster, while visualizing on the much smaller PLX. Since there was a 51 times 51 times 51 domain of velocity distribution data for each spatial point of the 128 times 128 times 128 space, it's quite apparent that there is a pretty decent amount of the data, more than 2 terabytes in total, for a single time step. So, if I wanted to view the velocity distribution of a single spatial point, I'd have to copy the whole 2 terabytes over, which would be really time consuming, especially if someone decided to rerun the simulation, generating a whole new dataset that would need copying as well. Thus, the general structure of the macro is 2 Python scripts, one on PLX, the other on Fermi, of which the former communicates with the latter via SSH. Other than a few curiosities such as the expectedly spherical distribution being more of a periodic filamented one due to a bug in a script that extracted the correct dataset from the correct file, written by one of the 1000 cores used, the process was quite straightforward after I got comfortable enough with the intimidating mess that Python scripts in PowerView can end up being, which, overall, was probably the most time-consuming part of the whole project. The finished script itself is almost ready to, for example, be packed up to be used for other projects in Seneca, which might find it helpful being able to visualize remote data on another cluster in a similar fashion.